So for this one, integral y(x) equals x min to x max of f of y(x) given I dyx. This is 1 minus the integral from minus infinity to x min of blah plus the integral from x max to infinity of blah. Excuse me, minus. It's 1 minus this, those are added together. And this guy is 1/2 c of, from minus infinity to x min, it's mean minus x min divided by root 2 times variance. So the mean is alpha I minus x min. This is just in the notes. And variance in this case is n0 over 2ts. So it's 2 times n0 over 2ts, and I get n0 over ts. This guy, integral from x max to infinity, I get 1/2 of c of x max minus alpha I divided by root n0 over ts. Okay, if you're wondering about how I managed to get that, just think of it this way. This tail is like the probability of error given that 0 was sent, where this is the mean and x min is the threshold. And this is like the probability of error given that 1 was sent, where alpha I is the mean and x max is the threshold. So if you just substitute in everything there, it all works out. So we get 1 minus 1/2 of c this minus 1/2 of c that. And similarly for the y, I get 1 minus 1/2 of c beta I minus y min over n0 over ts minus 1/2 of c of y max minus beta I over n0 over ts. So I won't bother writing it all together, but there's the answer. So 1 minus this guy times that guy. I will allow the rectangle to be infinite. So I said I have a rectangle like so. I will allow, for example, an infinite rectangle in one direction or even in two directions. Like that. That's perfectly fine. That basically means, in this case, it means x max is infinite. In this case, it means both x max and y max are infinite. Something like this would mean x max and y min. X min and y min are both minus infinity and so on. Okay, let's do an example. So here is my, here's what my signal will look like in signal space. So let's think back to the example I had originally. X and y, we can use those, sure, why not? So x is this, 1 over root 8, and y is this. Not really important. I'm just going to deal with signal space directly, but that's one example of x and y. Okay, so my points are, let's let n0 over ts equal 1. And then I'm going to say alpha I, excuse me, let n0 over ts equal 1 over square root of, okay, what am I doing? 1 over 4. And here are going to be my points in signal space. S0, S1, S2, S3. This is at point +1, +1. This is at point -1, -1. Excuse me, +1, -1. X is +1, Y is -1. This is at point -1, -1. And this is at point -1, +1. So let's calculate probability of error given that 0 is sent. That's this one. So my Voronoi region is this. It's an infinite rectangle with x min equal to what? 0. X max equal to what?
1.
It's infinity because it's an open rectangle. Y min equal to what? 0. And Y max okay, probability of error given 0 is 1 minus this times that. Let's call that 1 minus A times B. Where this is A and this is B. So A is equal to 1 minus 1/2 ERF C. Okay. Alpha I is +1, x min is 0, so that's 1 over root 1/4. Can I simplify that? 1 over root 1/4, 2. 1/2 ERF C 2 minus 1/2 ERF C. What do I have here? X max minus alpha. That's infinity minus 1, which is infinity. What do you think ERF C of infinity is? 0. 0. So that I can get rid of. B is 1 minus 1/2 ERF C. Okay, beta I is 1 minus Y min, which is 0. So that's 1 divided by root 1/4, so that's ERF C of 2. Minus 1/2 ERF C of Y max, which is infinity, minus B1, which is 1, which is infinity, which is 0. So B is equal to this. So basically I have this is equal to 1 minus 1/2 ERF C of 2 squared. So, probability of error given 0 is 1 minus 1/2 ERF C of 2 squared, which is 1 minus 1/2 times 0.0047 squared, which is, anybody got a calculator?
So 0.995.
This part, you mean? So it's 1 minus, is that with the square or without?
With the square.
With the square.